discuss some applications of these feedback control techniques because you want to use that for something, and I will show you some examples of where you can use them. Probably you have your own ideas already what to do with them. So the first one will be a physical one. It will address the active particle pressure, or the pressure active particles generate on a wall. The second one will be about the self-organization, which is actually due to information. And the third one, more or less related to a combination of these feedback control techniques with machine learning. So let's have a look at the first one. So the first one is interesting because it is some kind of basic law that if you have a container which is filled with passive particles or passive ions, or why, I don't know why I say ions, but atoms, then they have a thermal energy if they are in thermal equilibrium and they're causing a pressure. And that kind of pressure is denoted by the ideal gas law if you consider that as an ideal gas. Particles will bounce back from the wall and transfer some momentum, and due to the thermal energy they have and the density, they create a pressure on these walls here. This is something you learn in thermodynamics and statistical physics, of course. But on the other side, you can also create a system where you have a wall and you have these active particles. But now the active particles have a velocity which is not determined by the temperature. So it's a completely athermal process. Of course, this is now a non-equilibrium situation. And but still, the particles could bounce against the wall, and they are swimming against the wall, pushing, of course, liquid here and starting to pump. And by that create some kind of pressure. And you would not like to know what this kind of pressure is. And if this is a state function, for example, as here on the left side in the equilibrium case. So this kind of swim pressure could be actually very important, or is important, for the generation of these motility-induced phase transitions. So where we have at a certain density and a certain activity of the particles, the clustering into these kind of small droplets or crystals. But it turns out that the measurement of this active particle pressure is not really that easy. And one of the reasons why this is not that easy is that you have active particles at boundaries, at solid boundaries, and due to their hydrodynamic flow field they're generating, they are also creating a certain alignment of these particles in a very special way. And that could be heavily influenced also by the shape of the walls, finally. So what you don't want really is a pressure that depends on the shape of your container and some peculiar interactions of the particles with the walls. So what's the swim pressure now? And how to measure it is the question we would like to answer here in the following. So for that purpose, we have to look at some theory, the very basic equations only, and some of them you know already. So on the top left here, you see your beloved Langevin equations, which I showed various times already. So one for the overdamped case of the particle position, and one for the orientation measured here by an angle theta, which is the angle between the symmetry axis of the particle and the x direction here in that case. So one is giving rotational diffusion, one is translational diffusion plus propulsion, but in addition, you have now an additional term that is determined by the force that particles exert on the wall. And this is what actually causes the pressure, right? So without that term here in the middle, there would be nothing like a wall pressure. So of course, this is, as usual, describing everything nicely in terms of single particle trajectories, which might not be that useful. What you rather want to have is a flux balance. And the flux balances can be obtained from that by standard theoretical procedures, which is not my field, but you can obtain that. And it turns out that you get this kind of equation. So you get on the left side a zero, because at the wall the fluxes are actually zero. The fluxes are then determined by a diffusive flux, that kind of additional flux which is due to the force on the wall, and this kind of term which contains the velocity of the particles and an additional quantity which is p of x, which is the so-called local polarization. So the local polarization is nothing else than the local excess in particle orientations either towards or away from the wall if you are in one dimension. So if you just project everything onto this x-axis, you just measure the orientation of the particle with respect to the normal to that wall, which is the unit vector in the x direction. And then this is just the cosine of the angle theta I here. And the triangular brackets just denote that you average over time trace, or you average over an ensemble in that case, right? And that kind of quantity is then multiplied by the density, and there you get the polarization. So it tells you how many particles are rather pointing to the right than to the left if you have a certain density. This is the important quantity which enters now here, these fluxes. So that means also if you bring that here to the left side, you have these fluxes which determine the forces at a certain density on the wall, right? So by Newton's law, the integral over these forces is nothing else than a pressure. So if you convert the density by an integral, you have an areal density, and a force divided by an area is nothing else than a pressure. So this is the swim pressure we are actually interested in, more or less, except this kind of term is related just to gradients in the density and normal diffusion. So we'll neglect in the following this. I have to say that we also neglect any kind of interactions between the particles itself in this kind of equation, which is, however, in there here in this kind of paper by Solon from the Cates group, actually. So, so if you insert that kind of equation over there, which you should do, then you have one integral over this term here and one over that. This is what we wanted to neglect. And here it's essentially an integral over this polarization, which gives you the total polarization at the boundary. So this is the total polarization. And you see, if you multiply the total polarization times the velocity, you will get the pressure finally. So polarization times velocity is the pressure. And for an active particle system, you can measure that, or you can calculate that. It will turn out to be just the velocity of the active particles here in the bulk, multiplied by the density in the bulk, divided by 2 times the rotational diffusion coefficient. So this is the result for that kind of geometry with a wall. And now you have your recipe. That's the recipe to measure the pressure. You just need to measure the polarization. But of course, you don't want to do that on a wall where you have hydrodynamic interactions, because then everything is not anymore that easy. You want to have something where you don't have a wall, but still have a polarization. And the trick to do that is, of course, photon nudging, feedback control. And with that kind of technique, you can apply or create a rule which looks the following way, or these are several rules actually. First of all, you would like to create an arena in which you would like to measure the pressure, or the polarization essentially. And this is done by choosing this rectangular region, and whenever a particle leaves this rectangular region, then you just apply photon nudging to push that back, right? So this is here a photon nudging boundary. I told you already that it's perfect to confine particles. So these measurements with a single particle at the end take several days overall, all of the measurements together. So it's good to have them confined, the single particle, into the same region. And this rectangular region is then split into an active and a passive region. So in the active region, you switch globally the laser on. In the passive region, you switch globally the laser off. And whenever it crosses a certain line in your sample, you do that kind of switching. By doing that, you can create an active-passive boundary, which is extremely sharp, only has a uncertainty, which is roughly the localization accuracy of your particle in your experiment. So it's around 20 or so nanometers. So this is the trick you do, and to create a passive-active boundary where you would like to measure the polarization. And of course, for that purpose, you really have to know what your swimmer is doing very exactly. And that are some of the characteristics of our swimmer in the active and the passive region. So this is here the velocity, which is only existing in the active region. This is the rotational diffusion time in the active and the passive region. And the active region, you have some kind of additional effects due to radiation pressure. And this is the corresponding effective diffusion coefficient as a function of the velocity, which is shown here, right? So this is the passive diffusion coefficient you measure. Okay, So what you get as at first glance is something very easy. So if you monitor that region and you take all the trajectory points and plot all of the trajectory points to create an areal density of trajectory points, you see that they are much denser in the passive region than in the active region. And then you have this kind of fuzzy outside here, which is coming from the photon nudging. So if you integrate over the vertical direction, you get that kind of density profile. And you see the density is high in the passive region and low in the active region. And if you take the ratio between active and passive region densities, you resemble to find a law which was almost already found by Schnitzer, not completely. So in that case, it's given, the density ratio is given by the diffusion coefficient divided by the effective diffusion coefficient in the active area. So in principle, if both are active, this is the ratio of the effective diffusion coefficients. But since we have a passive one, then this is the passive, and this is the active region where you have here the active rotational diffusion time and the velocity. So if you do that for different velocities, you'll find that kind of data here, which nicely corresponds to the law here. So similar things have been obtained by Schnitzer already, but he was neglecting any kind of Brownian motion. So there's only the activity going in, and you have a problem if you switch off the activity completely. Yeah? So the other interesting thing is now that exactly at that boundary between the active and the passive region, you create this kind of polarization, which I mentioned before. So you have here a peak which goes to the negative, which means that you have more particles pointing to the left than particles pointing to the right, which is easy to understand, because if now diffusively a particle enters this boundary or comes to that boundary and points towards the right, so with a positive polarization, then this is immediately removed, while other particles coming from the right going to the left get stuck with the polarization here because they get passive in that kind of thing, right? So therefore you have here a negative polarization, and exactly this kind of polarization can now be analyzed in more detail. It will turn out that the polarization decays here on both sides exponentially with this kind of law here. So also in the active side, it's exponential. And this kind of exponential decay looks like the photon nudging sedimentation problem we actually had earlier. So the decay length will have to do something with the activity or the density. So the decay length actually ratio here of that exponential function here and that exponential function there is the same as the density ratio between the active and the passive side, right? And if you drive that even a bit further and integrate that over that kind of peak, so you determine the area here, below that you will find that the total polarization multiplied by the velocity gives you exactly that kind of pressure which we defined earlier for our swim pressure at the wall. So there we had the situation that we just had a wall which is against which the particles were pushing. Now we don't have anything where they are pushing against, but we have here this kind of bulk region with passive particles. And due to that boundary condition, we find actually the same expression here. So by integrating over that negative peak, we actually get the pressure, exactly that kind of swim pressure, and we can measure that without any kind of wall. But it is not really a pressure which is now exerted here on the passive side, but it's something which is equivalent to that if there would be a wall, because here particles are passing our wall. So this is a neat example, as far as I'm concerned, of showing you how you can use these feedback techniques to confine particles and measure some real physical quantity, which is otherwise difficult to measure. And you can do similar things also with the interaction of active particles when you confine 2 particles or 3 particles or 4 particles, for example, in a well-defined region, and then you have a single particle or 2 particle interactions, 3 body interactions, and all of these things which are interesting probably to theoreticians to be included in their simulations.